So hello everyone. In this video, let us look at exponential decay. So in the earlier videos, we have seen straight line and a cosine function. Today, let us look at exponential decay, which looks something like this: a exponential minus t by tau. Small t is the independent parameter. Tau and a are some numbers. So a is a multiplicative factor, and tau is a parameter which decides the decay, the nature of the decay. So in physics, we encounter two forms of equations. So one looks like this: a exponential minus x by b. So in this case, the b has same units as x, or another form which looks like y is equal to a exponential minus rx. So in such equation, 1 by r has same units of x, or r will have units of inverse of x. And in both the cases, a will have the same units or dimensions of y. So let's go to the simulation part. So let us select the exponential decay. And since there are two parameters, now remember in the discussion we have used some other parameters, exponential t by tau, but in this simulation, x is the independent parameter which will be plotted on this axis, and y will be plotted on this. So the function which we are going to use is a exponential minus x by b. So let us give some initial parameters: 1.25 for a and b as 2.19. So then let's say, so the function looks like this. So at the initial stage itself, we can see as x is increasing, the y is decreasing. So we'll see in more detail. Let us choose a parameter. Let us choose a. Yes, this is more easy to understand. So this function is plotted as 1.41 exponential minus x by 2.19. So we're trying to see what this parameter affects. So let us increase a. So a is about 3. Now it is going at x equal to 0. This function has gone up. So we can see the function is going up. So if all the way 0, so for all x it is 0. So let's put a small value, and at present it is 0.16. And let us see in comparison how does it look. So for 0.16 it looks like this. This is for 1.7. This is for 3.14, and this is for 5.037. So where is this number sitting? So looking at the equation, we should be in a position to see is there any special point related to this. So this phi happens to be at x equal to 0. What is the function value? It becomes the function value itself, because at x equal to 0, this uh, exponential term becomes 1, and then at x, the y value will be a itself. So the parameter a stands for the x value, the function value at x equal to 0. So let's leave it at that, and let us look at the parameter b. So let us choose b. So this is phi exponential minus x by 2.9. So let us change b, increase b rather. Observe what is happening to the function. Now remember, we are not changing a, so hence this point at x equal to 0 is remaining same. Observe that. Let's look in a compare mode. See, all of at x equal to 0, all of them has phi. But as b is decreasing, we can see the function is changing very fast. It's, b is almost 0. No, this b is almost 0. So we can see when b is very small, the value of y goes to 0 very quickly. And when b is high, the function value decreases very slowly. So as the name suggests, it is a decaying function. So at what rate it is decaying, the parameter b decides at what rate it is decreasing. So let us look at where it is. So for example, look at this function, phi exponential minus x by 4. So this b parameter, if you carefully look at it, at what value of x, the value of y becomes 1 by e. So we can see this at x equal to 4, when we put x equal to 4, this becomes exponential factor give us 1 by e. So it is 5 by e. So the 5 by e is 1.84. So you can see at 1.84, when y value is 1.84, the x value will be 4. So that is this parameter b. So to summarize, in the function a exponential minus x by b, the parameter a will be that value of y when x is equal to 0, and the parameter of b is that value of x when y becomes 1 by e of a. So let us look at some more properties. So we have seen this. So where do we encounter in physics? So again, there are many places where we encounter this. Table tries to summarize some of them. So you can see damping, nuclear decay, capacitor discharge, atomic emission, cooling law, evanescent waves, skin depth, frictions, and can be many more. So one important thing to look at is, what does this independent parameter stand? As you can see, in most of the cases, it is time, or it is related to length, depth, or displacement. And the parameters are gamma, lambda, tau, and many times if it is related to time, it will be tau, as in capacitor discharge, tau will be RC. And in nuclear decay, it is written as lambda t. So most of the time it is time, and sometimes it is length. So it has this parameter b has different names. Damping coefficient in damping, half-life, it is related to b by 0.69 by lambda. Capacitor discharge, it is known as time constant. In atomic emission, it is referred to as a lifetime. And 1 by a also has a name, transition probability. And in evanescent waves, it is attenuation coefficient, and in friction, it is friction coefficient. So the dimensions of b will be either related to time or length, depending on the way the function is written. It is either time or inverse time, length or inverse time. So coming to some general properties of graphs, in the last video for straight line and cosine, we had seen as x changes, what is remaining constant. We saw that it was slope, and in cosine, it was the separation between two maxima and minima was constant. And in exponential decay, there is nothing which is constant. Maxima or minima, straight line was not having any maxima or minima. Cosine has maxima or minima. In exponential decay, there is no maxima or minima. So is the function decreasing or increasing? So for a straight line, it depends on the slope. Cosine, it's oscillatory function. For exponential decay, it's always a decreasing function. And looking at exponential decay, there's one more thing we can add, asymptotic. So is there any point where the value of y becomes 0 or infinity? We can see at x equal to infinity, the value of function tends to 0, and at x equal to minus infinity, the value of the function tends to infinity. Whereas in case of straight line, straight line and cosine, there was no such thing. So that's all for this exponential decay function. Thank you. I hope you have enjoyed looking at the exponential decay visualization. Thank you.